Welcome to myprojectbuzzer.com. Here we discuss about the flexible low-power DSP with a programmable truncated multiplier. In this project, mainly focused on the truncated multiplier design. In this project, a new approach to truncation is proposed with the implementation of full precision multiplier and an active section of some partial product matrix, which is selected dynamically at runtime. A conventional approach to truncated includes physical reduction of a partial product matrix and a compensation for the reduced bits by a different compensation circuit. This results in optimization of fixed system for a given application at a decent time. The truncated multiplication process is also useful in reducing the power requirement for the computation process, since it computes only most significant bits of the product. This also allows a power reduction trade-off against a signal degradation to be modified at runtime. This makes the proposed architecture a hybrid one which consists of both the power reduction benefit from truncated multiplier and the flexibility of reconfigurable devices. This multiplier is presented in a customized digital signal processor in which software computation is introduced and enhanced. The system proposed in this paper is the first system-level DSP core using a fine-grained truncated multiplier. Software computation in this system is provided to be effective and with deployment of multiplier. There are several previous works developed for truncated multiplier. Among them, truncated multiplier based on Powerfully and both algorithms are mostly used in common. These structures by design do not compute the lowest sections of the partial product matrix. This process is not supported in reduction of power and also area. The majority of the previous publications focus on fixed width multiplier that produce a fixed bit output, and their gain versus error ratio is set by a hard. Now we discuss about the system flow diagram. The system flow diagram represents the flow of our process. First, we give the input signal to the input port. The input signal passes to the register and data memory block. The register generates the input signals randomly, and in our data memory block store in our input into the temporary values. The temporary values and shift registers values give it to the multiplier. The multiplier multiply the two input ports. The multiplier bits output passed into the accumulator. The accumulator adds all the multiplier outputs. Then finally generate our outputs, and the register and accumulator controlled by the control unit. The control unit mainly based on our select bit. Here we are going to discuss about running procedure of our project. In this process we have four steps. First step, we check the syntax error. Then second step, we generate the RTL schematic diagram. Then third step, we generate the technology schematic diagram. Then finally we generate the simulation waveform. Now we are going to the first step. First select the implementation and then check the syntax error. Please select check syntax and run the process. In this step, we check the syntax error. In case of any error and warning is there, displayed in our console block. Now in our process we have no error. Therefore we are going to the second step. We please select the RTL schematic and run the process and add and create a schematic. This is our overall RTL schematic diagram. Cin flags are our input signals. Now we are going to the third step. Please select view technology schematic and run the process and add and create a schematic. This is our overall technology schematic diagram. Now we are going to the final step of our project. Please select simulation and click the simulate behavior model. In this process, we give the input signal as text file. Please show in our code folder. S1 and S2 are our input values, and our output values are placed in our out text file. We have no output text file. Our input we give the input at -64. Our second input are 45. Now we are going to the multiplier of -64 and 45. Now we give the initial state, clock value set to 0. Please run. Please show our input value 1. This is our 2's complement value of our 64, and input 2 represented the 44 value. In our project, please change the clock signals simultaneously. First of all, we give the initial condition to clock value, clock set to 0. In this step, the real number convert to the binary value. Our input signal represented at 11000000. This value represent to 64. Our signed bit represented at output. First bit represents signed bit, remaining bit represents our input signals. Then our second input 45 convert to binary value 00101101. In this step we have no signed bit, therefore it represented 0. In case of any doubts are there, please check the decimal to binary value conversions. Then next change the clock value to 1. Then again change the clock value to 0. Then again change the clock value to 1. Finally, we got the output signals. Please show our final output at our out text file. Please select our out text files. Now we got our output. Please verify our output. This is our running procedure of our project. Thank you.